Hello and welcome everyone back to the fifth lecture on vector space. So in this video we are going to talk about some extra problems on basis and dimension, the topic that we have discussed in our previous lecture. So we will be solving a few problems on that, and then lastly we will be discussing replacement theorem. Okay, so let's start with the problems of basis and dimension. It is given that W is a subspace of R3, the vector space R3, where W is given by something like this. That means W is set of all those real three-dimensional coordinates whose sum of the coordinates is 0. Okay, and we need to find the basis and dimension of this subspace. Okay, so it's already told it's a subspace, so we don't have to prove that it's a subspace. So W is itself a vector space and we need to find its basis and dimension. Okay, so let's see how we can solve these kind of problems. In order to show, or in order to find the basis of W, our target is to find a set, let's say S. Okay, I am telling you the rules of doing the sum, the process. We will be finding a set S and we will be trying to show that L of S is equals to W and S is linearly independent. Okay, these are the two things that we will be trying to do. So if we are able to find such a set which generates W and which is linearly independent, then that set becomes the basis and the number of elements in that set becomes the dimension. Okay, now the question is how to find this set S. Okay, remember, from the condition which is given to you, try to eliminate as many variables as possible. Okay, try to reduce the number of variables using the conditions given to you. So here I have only one condition, so that means I can reduce only one variable. What I mean to say is that I have x plus y plus z equals 0. So from here I can eliminate any one variable, whichever one I want, either x or y or z. So let's say I am eliminating z, then I will have z equals to minus x minus y. So that means any element of W is going to look like x comma y comma, instead of z I'll write minus x minus y. So maximum I am able to remove only one variable. Okay, so now let's start with a random element of W. Okay, let's say that let eta belongs to W. Okay, then eta would be looking like a comma b comma, instead of taking the third coordinate as c, we can write the third coordinate in this manner. So it would be minus a minus b. Okay, written in this manner. So this is some random element of W. Okay, now I want to show that this random element that I've taken, so first let me construct the S set, then I will be able to say such things. So I will be taking the variables that I have, which is a and b, I will take them common. Okay, so if I take a common, I have a over here and a over here. So if I take a common, I'll have 1. Since I don't have any a in the second element, so that's going to be 0. Another a in the third element with a coefficient of minus 1, so I'll have minus 1. Plus, now if I take a b common, I don't have any b in the first term, so that's going to be 0. 1b in the second term, so that's going to be 1, and another b in the second term with a minus coefficient, so that would be minus 1. Okay, let me call this element as alpha and let me call this element as beta. Okay, so now how are we going to construct the S set? The S set is going to be the set containing this alpha and beta which I have constructed over here. So this is the process of constructing the set. Now I will just go on to show that S is linearly independent and S generates W. Hence the set S is going to become a basis, and since the basis contains two elements, its dimension is going to be 2. Okay, so now it's going to be a simple process. But how did I make the S set? First objective is try to reduce the number of variables from the given condition. Since only one condition is given, so I could remove only one variable. I removed the third one, so I had two variables. So I cannot further reduce the two variables. So now take the variables common, whatever element you get, give that a name alpha, beta, and construct your required S set out of it. Okay. So now I'll say that let S equals to alpha comma beta. Okay, where alpha is 1 0 minus 1 and beta is 0 1 minus 1. Okay, so I have got my S set. So now let me quickly show that S is linearly independent. The second one is easy to show. Here you can see that I don't need to use the proper definition of linear independence. When I am dealing with only two particular elements, it's actually very easy to show whether they are independent or dependent. That is by saying that alpha cannot be expressed as any scalar multiple of beta, which means it is linearly independent. Because if two vectors or n number of vectors are linearly dependent, then any one vector can be expressed as a linear combination of the remaining vectors. Okay, so here I have two vectors. So if the first one can be expressed as a linear combination of the second one, which means if the first one can be expressed as a scalar multiple of the second one, then they are dependent. So if that is not happening, then they are independent. So you can just observe that if you multiply any scalar with the first one, you will not get the second one, or if you multiply any scalar with the second one, you will not get the first one. So it's not going to happen. So we will say that here S is linearly independent since alpha not equals to C beta for any C belongs to real numbers. Okay, so alpha cannot be expressed as any scalar multiple of beta, and neither in the opposite way that beta cannot be expressed as a scalar multiple of alpha. Okay, so I have got the first thing, which is linearly independent. Now I want to show L of S is equals to W. Okay, so if I want to show, now my target is to show L of S is equals to W. So for that I'll show this in two steps. The first one, I'll show that L of S is subset of W, and second one, I'll show that W is subset of L of S. So these are the two things that I will show, and hence I'll be able to conclude that L of S is equals to W. Okay, so let me start with the second one. Okay, that means I'll take an arbitrary element from here, let's say Xi, and I'll show that Xi belongs to L of S. Okay, so let actually I don't need to show this one explicitly. I've already got the expression here. Okay, let me call the arbitrary element to be eta. Okay, instead of Xi, let me call it to be eta. Then you can see I have already expressed eta as a linear combination of alpha and beta in this line, right? I have already expressed that eta is equals to A times alpha plus B times beta. Okay, so that means alpha and beta, they are linear combination. Eta is a linear combination of alpha and beta. So this implies eta is a linear combination of alpha and beta, which belongs to S set. So linear combination of the elements of S. Okay, so since eta is randomly taken from the W set, so that means over here I can say that eta belongs to L of S and it is randomly taken from W. So therefore eta belongs to W implies eta belongs to L of S, which means W subset of L of S. Okay, so I have got my second criteria here. Okay, that W is subset of L of S. Now I want to show the opposite thing is also happening, that L of S is subset of W. Now I will try to show that L of S subset of W. Okay, now S contains the elements alpha and beta. Okay, so if I take L of S, and obviously we know that this is subset of W because alpha and beta both belongs to W. You can check over here the property of belonging to W was sum of the coordinates had to be 0. So here the elements of S are alpha and beta. You can see that sum of the elements in alpha is 0 and sum of the elements in beta is also 0. So obviously these alpha and beta, these are elements of W. Okay, so I can say that it's a subset of W. Now I'll just use a property I have defined much before in my previous lectures, that if S is subset of T, then L of S is subset of L of T, right? And more importantly, if the right hand side set, if any of the right hand side or left hand side, doesn't matter, if any of the set is a vector space in itself, is itself a vector space, then it is not required to write L of T, then it's just enough to write only T, right? Because L of any vector space is the vector space itself, right? So here W is a vector space and S is just a set. So if I take L on both sides, so I'll have L of S subset of L of W, and L of W means W itself, since W is a vector space. Okay, so I have got my second requirement here. Okay, so I got both these requirements from 1 and 2. Okay, I can say that Ls is equals to W. Okay, so from this 2 I can say that this implies Ls equals W. So previously I had got that S was linearly independent. Now I have got L of S is equals to W. So I have got the two requirements for S to form a basis. Okay, so I can say that therefore S is linearly independent and L of S is equals to W, and this implies S is a basis of W. And since S contains how many elements? 2 elements, alpha and beta. So this implies dimension of W is equals 2. Okay, so that's the answer to these kind of questions. Let's take a look at another kind of question. Here the difference between this question and the previous one is we have two conditions. Okay, in the previous question we had only one condition. Now whenever more than one condition is given to you, look at the conditions and try to understand that are both the equations different, or if I multiply any constant with the first equation, will I get the second one? Okay, that's something you need to understand. If this thing is happening, that if I multiply something with the first one, I get the second one, that means the second equation is not at all required in the question, right? Only the first one would be enough, because the first one is written in a repetitive manner in the second one. Okay, so in that case only the first equation would be sufficient, and then the question would go back to the previous problem where I have only one condition and 3 variables. Okay, so 3 variables, 1 condition. So if you subtract them, 3 variables and 1 condition, you get a dimension, you get dimension 2 and a basis containing 2 vectors. Okay, but if the two given conditions are both required, they are both different from each other. Okay, as per this question, this condition and this condition are both completely different. They are not scalar multiples of each other. So in this question I have again 3 variables and 2 sufficient conditions. Okay, 2 conditions. So 3 minus 2, it would be 1. So that means my basis will contain only 1 vector and the dimension will be 1. Okay, that's the simple logic. Alright, so let's get started. As per the previous question, we'll follow the same process. We'll try to eliminate as many variables as possible. So here, since you have 2 equations and 3 variables, you will be able to eliminate 2 of the variables. Okay, so let's try to eliminate 2 variables from these 2 equations. Okay, let me find the value of x from the first one. So x would be minus z minus 2y, and I'll substitute that in the second one, and I'll get 2 times minus z minus 2y plus y plus 3z equals 0. So that would turn out to be minus 4y and plus y would be minus 3y, minus 2y and minus 2z and plus 3z would be plus z equals 0. So I have z equals 3y. Okay, I have got z equals 3y, and let me say that this is equals to some constant k, okay, or some constant I can assume 3k. Okay, just for convenience I'm considering that let this be equals to 3k. Okay, so then I would have z equals 3k and y equals k. Right, individually if I take z equals 3k and 3y equals to 3k, then I get these two things, and I have no condition on x, right, because if I try to put this value over here, it's going to be 0, right. If I try to put it here, it's going to be 0. So I have exactly got the value of x, z and y in terms of k, and I don't have any condition on x. Okay, now I will put these two values in place of x and get the value of x from here. So this would give me that x is equals to minus of z, so that's minus 3k, and minus of 2y, that's minus 2k. So the value of x would be minus 5k. Okay, so I've got the value of x, y and z in terms of some constant which I've taken as k. So I can say that therefore the coordinate x, y, z is becoming minus 5k, k and 3k. So I can easily take the k common and I'll have minus 5, 1, 3. Okay, so this is how an element of the W subspace would look like, where k is any constant. Okay, so as you can see, I told you I have two sufficient equations. Okay, both are different from each other, so that means I can eliminate two of the variables. So I've eliminated two variables and my final answer is in terms of only one variable, which is looking like k right now. Okay, so the coordinate can be expressed as a function of one variable. The other two variables have been eliminated. Okay, so again now the same process is going to continue. I'll take a random element from W. So let eta belongs to W. So this would mean eta would be looking like k times minus 5, 1, 3 for some k belongs to real numbers. Okay, and you can obviously see that since I have found out this value by solving the two equations in the given question, in the given criteria for finding W, so obviously this element is belongs to W. Okay, so obviously this element belongs to W, because if you take this minus 5, 1, 3 and put it in the two equations, obviously they will satisfy, because I've got this value by solving the equations only. So that means this is an element of W for whatever value of k I choose, does not matter. Okay, so let me call this element as alpha. Let me call that, let minus 5, 1, 3 equals alpha, and let S be the set containing only alpha. So S is basically the basis set which I'm trying to construct here. So you can see that eta can be expressed as a scalar multiple of alpha. Okay, so here we have eta is equals to a scalar multiple of alpha. So which means eta belongs to L of S, right? And eta was taken from W, and ultimately eta is belonging to L of S. So I can say that therefore W subset of L of S. Okay, so that's the first criteria which I needed to find out. Now I need to go the opposite way, that means L of S subset of W I need to show. So again the same way as before, S is the set containing alpha, which definitely belongs to W, as I showed you over here that it belongs to W, so that means it's a subset of W. So now if I take L on both sides, so L of S will be subset of L of W, and L of W means the set W itself, right? So this is my number 2 criteria. From 1 and 2 I can say that L of S is equals to W, and that becomes my first criteria for forming a basis. And now the second criteria was linearly independent. As you can see, S contains only one element, that means S is a singleton set, right? S is a singleton set, and we know that every singleton set is definitely linearly independent. Okay, so I can say that since S is singleton set, this implies S is linearly independent, and this becomes criteria number 2 for basis. Okay, so from criteria 1 and 2 I can say that therefore S is the basis of W, and dimension of W, that would be how much? S contains only one element, so dimension is 1. Okay, so that's the proof, or that's the answer to this question. And I had already claimed even before starting the question that its basis is going to contain one element and its dimension is going to be 1. And how did I tell you? It had 3 variables, 2 unique conditions. So it's variable minus unique conditions gives you the dimension directly. Okay, going to another kind of question here. It's saying that find the basis and dimension of the subspace S, where S is given by set of all 2 cross 2 real symmetric matrices. So here the conditions are not given to us explicitly. In the previous 2 questions the conditions were given. Here only a statement is given to us. We need to convert this statement into a mathematical equation format. Okay, now the thing is, how can I express set of all 2 cross 2 matrices by writing it explicitly? Achha, how does a real symmetric matrix look like? That's the first question we need to understand. We know the property of real symmetric matrices is A equals A transpose. The transpose of the matrix is equals to the original matrix. Achha, so we have 2 cross 2 matrices. So that means if I have A, B, C, D as one of my 2 cross 2 matrix, if that's the A matrix, and if A is supposed to be equals to A transpose, now A transpose would be A, B, C, D, so that's A transpose. And if both are supposed to be equal, okay, if A has to be equal to A transpose, then I need to have A, B, C, D equals to A, B, C, D in this way. So you can see that the A and the D, they are both matching, but what is not matching is B has to be equal to C. So my condition is B has to be equal to C and C has to be equal to B. Okay, so that means for a real symmetric matrix, the cross diagonal elements has to be both equal. B has to be equal to C and C has to be equal to B. So basically the same thing, so which actually means the cross diagonal elements has to be same. So if I take any matrix of this format, the diagonal elements doesn't matter. As you can see, the diagonal elements don't matter. I take whatever diagonal elements, and the cross diagonal ones, whatever I take, I just need to make sure that they are both equal. Let me call that C. So A and B in the diagonal and the same element in the cross diagonal. Okay, so this is definitely a real symmetric matrix, 2 cross 2 real symmetric matrix. Okay, so this is the expression, or this is the condition you need to remember. I just showed you explicitly how that is happening, but you just need to remember that for a real symmetric matrix, any diagonal element you can take, the cross diagonal has to be same. Okay, so I'll just start from there, that in a set of 2 cross 2 real symmetric matrix, this set can be expressed in this particular format: A, B, C, C belongs to R 2 cross 2 such that A, B, C belongs to real numbers. Okay, so this, instead of giving us this condition, the statement was given. So from the statement I created the required condition of the question. Okay, so now you have to observe how many variables are here, independent variables are here. A is completely an independent variable, it can be any value. B is completely an independent variable, it can be any value. And again C is an independent variable, it can be any value. Okay, so how many independent variables? A, B and C, 3 independent variables. And I cannot reduce these variables. I have already reduced it. Instead of taking A, B, C, D, I have taken A, B, C and C in the cross diagonal. So I have reduced the number of variables, and it's after reduction there are 3 variables. So that means the basis is going to contain 3 elements and its dimension is going to be 3. Okay, so let's just find that out right now. Now, as we were doing in the previous questions, okay, it's just like the same process that you using the conditions, you try to remove the variables and get some constant element which you call as alpha. So here also we'll be trying to do that. Okay, so firstly I'll take a random element from S. I'll say that let eta belongs to S, so that means eta would be looking like A, C, C, B, and I will actually want to take the independent variables common out of it. So if I take A common, I have A only in the first position, the rest I don't have any A, so 1 0 0 0. If I take B common, then on B is only in the 4th place, so 0 0 0 1. And if I take C common, I have 0 1 1 0. Okay, so this element I'm going to call as alpha, this as beta, and this as gamma. So these 3 matrices I'm going to give them the name alpha, beta and gamma. Okay, so, and put them in a set and name it S, and ultimately show that S is the basis. Okay, so I'll say that let S equals alpha, beta, gamma, where alpha is 1 0 0 0, beta is 0 0 0 1, and gamma is 0 1 1 0. Okay, so I've created my S set. Now I just need to show that this is the basis. Okay, now first of all I need to show it is linearly independent. So since I have got 3 elements here, so I cannot just say it like that. I need to use my definition of linear independence. So I take that let C1 alpha plus C2 beta plus C3 gamma equals theta, and for linearly independent I need to show that all the 3 constants has to be mandatorily 0. Okay, so that means C1 1 0 0 0 plus C2 0 0 0 1 plus C3 0 1 1 0 equals theta. So in this case theta would be 0 0 0 0. From here let me construct the equations, taking the first position, C1 into 1, C2 into 0, C3 into 0 is equals 0. Okay, so I'll have C1 equals 0. Achha, now if I take the second multiplication, which means C1 into 0, C2 into 0, C3 into 1 equals to this 0. So then I would get C3 equals 0. And finally if I take this multiplication, C1 into 0, C2 into 0, C3 into 0 and this 0, then I would get C2 equals 0. So as you can see, I have got all the 3 variables mandatorily 0. So from this expression, if I get all the 3 constants C1, C2, C3 to be 0, that means S is linearly independent. Okay, so I can say that therefore S is linearly independent, and that's the first required property for forming a basis. Now going on to the next one, where I need to show L of S is equals to, Achha, I think I have named my set as S, and in the given question also it was S, so that will be creating some confusion. So let me just change this and call this W. Okay, so I am changing the original question name of the subspace as W, so that would, you know, just remove the confusion from the question. So I will call this W, and now my S set construction is fine. So now this S and the question's S don't match with each other, so now that's just fine. Okay, so I have basically got that my S set is linearly independent, that's fine. Now I need to show that L of S is equals to W. Okay, so again, proceeding in that same way like we have done before, S contains the elements alpha, beta, gamma, and if you check each of the elements alpha, beta, gamma, each of those matrices are definitely symmetric matrices, right? Because the cross diagonal elements are same, the cross diagonal elements are same, the cross diagonal elements are same. So therefore alpha, beta, gamma, all of them are symmetric matrices, and hence all of them belong to my W subspace. Okay, so this is subset of W. So if I take L on both sides, I'll have LS subset of L of W, which means simply W. So that's one of the conditions I need, and then I need to take a random element from W. So that calculation I have already done before, right over here. Okay, so I'll be just copying down this line, down there. So from that expression I'll be able to say that I have already got eta equals A alpha plus B beta plus C gamma, where eta was a random element taken from W. Okay, so from this expression we can just say that eta belongs to linear combination of the elements of S, because alpha, beta and gamma are the elements of S. So eta was taken from W and eta is ultimately belonging to L of S. So I can say therefore W eta belongs to W implies eta belongs to L of S, and that means W subset of L of S, and that's the required second condition. So from condition number 1 and condition number 2 I can say that L of S is equals to W, and that's my second required condition for basis. Okay, so using the first condition, which is linearly independent, and the second one, which is L of S equals to W, I can say that S has become the basis of W. So therefore S is the basis of W, and dimension of W is 3, because it contains 3 elements alpha, beta and gamma. Okay, so these are all the different kinds of questions of basis and dimension that we have done. Now we will move on to replacement theorem. Now continuing to replacement theorem, it is saying that if I have a set of vectors alpha 1 to alpha n, and it is a basis of a vector space V over a field F, and beta, vector beta, it is a vector from the vector space V, and beta can be expressed in this format. That means beta is expressed as some linear combination of the elements of the basis, which is obvious. In this expression, okay, in this expression, if any at one of the constants is non-zero, okay, if any one of the Cj is non-zero, particularly if I say that the jth element is non-zero, then in the jth position of these elements alpha 1 to alpha n, in the jth position I have the element alpha j, then I will be replacing alpha j by the beta element. Rest of the elements are going to remain same. So as you can see, up till alpha j minus 1 I have the same previous elements. Continuing from j plus 1 I have the same elements again, only in place of alpha j I have replaced it with beta. Okay, then I'm going to say that this also forms a new basis of the vector space. Okay, so the previous one was a given basis, this is again a new basis. Okay, so this process of replacing a certain element from the basis by another element and still forming a new basis, this process is called replacement theorem. Okay, so now let's just name the two sets for our convenience. Let me say that this is the set S and this is the set T. Okay, so it is given to me that S is a basis. If beta can be expressed in this manner, and in that expression if the jth element is non-zero, then I can replace beta with the jth element of the basis and form a new basis. Okay, so let's go into the proof of this. So I need to prove that T is a basis of the vector space V. So if I have to prove T is a vector space, I have to show, if T is a basis, if I have to prove, then I have to show two things. The first one is I have to show it is linearly independent. The second one is I have to show that the linear span of T generates the entire vector space. Okay, so the two things that I need to prove, I am writing it over here. Number one, I want to show that T is linearly independent, and number two, I want to show that L of T equals the vector space V. So these are the two things that I want to prove in this theorem. Okay, so first let me start with the linearly independent part. Achha, now for linearly independent, I am going to use the definition that I am going to consider, let already the C's are already used. I'm not going to use C, I'm going to use some other constants. Let's say D1 alpha 1 plus D2 alpha 2 plus taking all the linear combination of all the elements of T. So like this, I will be reaching Dj minus 1 alpha j minus 1. Then I have the beta element. So Dj into beta. I'm going to erase this off, and then I have dj plus 1 beta j plus 1, and again this is going to continue up till alpha n element. So plus dn alpha n. So I am going to consider that let this be equals to theta. Okay, and if I want to show that it is linearly independent, I need to show that specifically all the di's are 0, right? So I need to mention that where the di's are taken from field for all I 1 to n. Okay, and so now in place of this beta, I can substitute this given expression. Okay, so I'm just substituting this given expression in place of beta. So that means I'll be having d1 alpha 1, d2 alpha 2, and this will go on up till dj minus 1 alpha j minus 1 plus dj into, now the beta element, I'll write that with a different color. That's going to be this element, right? This substitution, which is c1 alpha 1 plus c2 alpha 2 plus dot dot. Achha, I will be writing it in a more explicit way. That means I want to write the jth element also to make it easy, my calculation. So I'm writing the j minus 1th element, which will be cj minus 1 alpha j minus 1 plus cj alpha j plus cj plus 1 alpha j plus 1 plus dot dot. This will go on until cn alpha n. So that's the substitution for the beta element. Then again we are continuing with what we had, dj plus 1 beta j plus 1. Sorry, I think this should have been alpha j plus 1. Okay, this is not beta, this was supposed to be alpha j plus 1, so that was a writing error, just ignore that. dj plus 1 alpha j plus 1 plus dot dot dn alpha n equals theta. Okay, so in place of the beta, I have substituted its given value. Rest of the elements are remaining as it is. Okay, now I want to club all the elements together, taking the alphas common. Okay, so now I want to take alpha 1 common and see whatever constants I'm getting. As you can see, the coefficients of alpha are d1 and over here dj into c1. Okay, So d1 plus dj c1, that's the coefficient of alpha 1. Coming to alpha 2, you can see the coefficient of alpha 2 is d2, and out here I'll be getting dj c2. So d2 plus dj c2 plus, like this it will continue. I am directly coming to the alpha j minus 1 element. So alpha j minus 1, just similarly it will have the coefficient dj minus 1, cj minus 1 into dj, right? So dj minus 1 plus dj into cj minus 1. Okay, now coming to the jth element, which is alpha j, and you can see there is no alpha j outside the bracket. There is only one alpha j which is present over here. There is no other alpha j element in the entire expression. So the coefficient of alpha j is only cj and nothing else. Okay, again when I move on to alpha j plus 1, again similarly I'll get two elements, one from inside the bracket, one from outside the bracket. So the moment I come to alpha j plus 1, now again I have over here dj into I missed the dj outside over here. I missed the dj. It should have been dj cj. Okay, so dj into cj plus 1. So dj j into cj plus 1, and outside I have dj plus 1. And like this, the same pattern will go on until I reach alpha n. So plus alpha n, if I take common, one alpha n coefficient I'll have inside, which is dj cn, and from the outside bracket I'll have dn. Okay, now the important thing to observe here is that what are the vectors we are having. Okay, what are the vectors? I'll just mark them with a different color. Just observe the vectors are alpha 1, alpha 2, alpha j minus 1, alpha j plus 1, and going up till alpha n. So basically starting from alpha 1 up till alpha n, and these are some coefficients of those alphas, right? So this expression is something very much similar to alpha c1 alpha 1, c2 alpha 2 plus dot dot cn alpha n equals theta. Okay, so I'm just writing it in a rough manner that this expression is almost similar to something like this: some constant into alpha 1, some constant into alpha 2, up till some constant into alpha n equals theta. Okay, and what are these elements, alpha 1, alpha 2, alpha n? These are the elements of the set S, right? These are the elements of set S, and it is told that S is already a basis. It is told S is already a basis. That means the set S is definitely linearly independent because S is a basis. So if S is a basis and it is linearly independent, that means if I take this kind of an expression, the linear combination of all the elements of a basis equals theta, then from this expression what we get is all the constants should be identically equal to 0, right, up till Cn equals 0, right. So this is the condition we get from linearly independent set of vectors. So I can use this condition in the equation that I have got over here. So in this expression I can say that all these constants have to be identically equal to 0 as per the condition of linearly independent vectors, right. So all these underlined constants, they have to be equal to 0. Okay, so now I am using that condition, that since the set S is a basis, this implies S is linearly independent, and that would finally imply that all these coefficients must be equals to 0. That means d1 plus dj c1 equals d2 plus dj c2 equals going up till I'm directly coming to the jth minus 1th element, which is dj minus 1 plus dj cj minus 1 equals to the jth element, that's a different constant, so that is dj cj equals to, again continuing the same way, dj plus 1 plus dj cj plus 1 equals to going until dn plus dj cn, and all of them must be equal to 0. Okay, so I am now specifically concerned with this particular part, that dj cj is equals to 0. Okay, all of them are 0. Initially I am concerned with dj cj equals to 0. So you can see that since dj cj equals to 0, that's something I've got. This must imply that specifically dj has to be 0 because cj is non-zero. Now why is it non-zero? See, that condition is already told to me in the question, that corresponding to cj not equals to 0, the specific jth element not equals to 0, we are doing the replacement. Okay, so since the jth element cj is non-zero, so therefore I can say that since cj is non-zero, dj has to be 0. Okay, now if dj is 0, just look at the first part. Suppose if I take this one, then d1 plus dj c1, we know this is already 0, where dj is 0. So if dj is 0, this would give me d1 equals to 0, right, if the dj part is 0. Similarly, if I take the second one, I have d2 plus dj c2 equals 0. Again, if I take dj equals to 0, that means if this part is 0, I will be getting d2 equals to 0. So like this, from each of the expressions, if I put dj equals to 0, so like this would go on, and finally I would get from the last expression that dn plus dj cn equals 0, that would imply dn equals 0, right? So I am getting all the di's to be strictly 0, right? Achha. So I'll just write it over here what I have got. So I've got, therefore d1 equals d2 equals all the constants including the j minus 1, j plus 1, all those elements up till dn, all the constants are 0, and this is something that we have got. Okay, now this thing is going to be important for our starting line. See, in our starting line I had taken the constants d1, d2, dj minus 1, dj plus 1 up till dn equals theta, right? So if in this expression, if all the coefficients turn out to be equal to 0, that means these vectors alpha 1, alpha 2, alpha j minus 1, beta, alpha j plus 1, alpha n, this set of vectors must be linearly independent, right? Because in this expression, if all the coefficients become equal to 0, that means the vector set must be the linearly independent set. So this vector set that I have circled over here, alpha 1 up till alpha j minus 1, then beta, then starting from alpha j plus 1 to alpha n, this set was termed as the T set. As you remember, I had termed this as the T set. So it turns out that this T set is linearly independent, which was the first part of our proof, because we are trying to show T is a basis. So we had to show T is linearly independent, and that we have got it just now, right? So I'll mention it over here that this implies T is linearly independent, and let me call this as number 1. Okay, so this is one of the criteria of basis that we have already got. Okay, now our next target is to show that the T set generates the vector space V, because we are trying to show T is a basis. Okay, So now our next target is to show L of t equals to the vector space. Achha, so how can we start with that? We will start with the given expression. See, this expression was given to us, that it was given beta equals c1 alpha 1 plus c2 alpha 2 plus dot dot going up till cn alpha n, right? This expression was given to us. Achha, I'll write this expression in a more better way. Okay, I'll not directly jump to the nth element. I will write the j minus 1th element followed by the jth element followed by the j plus 1th element, and then I will finally go on to the nth element. Okay, now in this expression I want to keep this term on the right side and bring everything else on the left side. Okay, so I want to keep this term on one side. That means I want to keep cj alpha j on one side of the equation and take everything else on the other side. So if I take c1 alpha 1 on the other side, I will be having minus c1 alpha 1, then the next one would be minus c2 alpha 2. Like this it would go on up till cj minus 1 alpha j minus 1. Then the next one would be this one, but instead of jumping from here to there, I will now write the beta element. So I'm bringing all the elements one by one on the left. Okay, like this, all the elements I'm bringing to the left. After I brought all these terms to the left hand side, the beta element was already there, so I'll write the beta over here, so plus beta. Then again I'll start bringing the other elements from the right hand side to the left, so I will have minus cj plus 1 alpha j plus 1, and this process would go on up till the nth element, which is minus cn alpha n. Okay, achha. Now it was given to us that the cj element is specifically non-zero. Okay, it was given that cj not equals 0. So I'm going to use that expression, that cj not equals to 0, and try to bring some help out of that. Okay, so we have cj not equals 0. So if some field element is non-zero, that means its inverse exists in the field. And what's the property of inverse? We know the property is such that cj composed with cj inverse, in this case the composition is multiplication. Okay, we are dealing with the binary composition as addition and the external composition as multiplication. So this is the external composition, which is multiplication. So cj, the inverse of cj being cj minus 1, if I compose them, I'm going to get the multiplicative identity, which is 1, right? So the inverse cj not equal to 0 would imply that cj multiplied with its inverse would give me 1, which is quite obvious. So in this expression, I am multiplying the entire expression by cj inverse. Okay, so I'm multiplying by cj inverse. So as you can see, I already have cj on this side. Achha, now another thing, it does not matter if I'm multiplying the inverse from the left side or from the right side. From whichever side I multiply, I should be getting 1, right? So now I'm multiplying cj inverse on the entire expression from the left hand side. So this element would be cj inverse multiplied with cj, so it would become 1. So alpha j would be remaining, and with the other elements I'll keep the multiplication as it is, which is minus of cj inverse c1 alpha 1 minus of cj inverse c2 alpha 2, and like this it would go on with all the elements, minus cj inverse cj minus 1 alpha j minus 1. Then I have the beta element, so plus cj inverse beta minus cj inverse cj plus 1 alpha j plus 1, and like this it would go on up till the nth element, so minus dot dot cj inverse cn alpha n. Okay, so I multiplied cj inverse with all the elements. Now let me call this constant by a different name. Similarly, this constant, including the minus sign, okay, including the minus sign, let me call these, give these constants a more simpler name. instead of writing it in a so much explicit manner. Okay, so let me say that alpha j is equals to, let me call this let's say T1, the next one let me call it T2. So since I have already taken the minus sign, so it will be a plus T2 plus dot dot going up till Tj minus 1 alpha j minus 1. And then this is a little bit different. All the constants are in a certain pattern, only Cj inverse is not matching that pattern, the coefficient of beta, but still we are going to call this element as per the name we are going, T1, T2, Tj minus 1. So the next one should be Tj, so Tj beta plus Tj plus 1 alpha j plus 1 plus the last one would be Tn alpha n. So I need to explain what are my substitutions, where I should say that Ti is, if I name the ith element would be minus Cj inverse Ci. Now remember, this is working for all the elements except particularly this one which does not match the pattern. So I should mention that for all I equals 1 to j minus 1, there is a jump in the jth element because the jth element is not matching the pattern. So again continuing from j plus 1 and going on up till n. So this pattern is for all the elements except the jth one, and particularly Tjth element is simply Cj inverse. Okay. So this pattern is for all the elements except the jth element, and the jth element is specifically like that. And I can say that, and Ti belongs to field, since all these are elements of field, so all these compositions are definitely going to belong to field. So Ti belongs to field. Now this is going to happen for all the i's, right, for 1 to n. Okay, so I have now got this expression. So let me write this expression one more line, and that alpha j equals T1 alpha 1. Now instead of breaking it in this manner over here, I actually need to break it, it's not a problem. So I'll just freshly write that again. So instead of writing the equation from this expression, what I can write in words, okay, I want to write it in words, that you can observe that alpha j is a linear combination of the elements of alpha 1, alpha 2 going up till alpha j minus 1, beta, then again continuing from alpha j plus 1 till alpha n. So alpha j is a linear combination of the elements of these vectors that I have circled, and these are the vectors of the T set, capital T set, right? So I can say that alpha j is a linear combination of the elements of the capital T set. Okay, so now from here I am going to draw the conclusion that I am trying to show, that L of t is equals to V. From here I am going to draw the conclusion. Okay, I'll do one thing, I'll just write the S set and the T set one above the other so that it's easy to understand what's happening. Okay, the S set is alpha 1, alpha 2, alpha j minus 1, alpha j plus 1, and going up till alpha n. And the T set is alpha 1, alpha 2, alpha j minus 1. Instead of alpha j we are having beta, alpha j plus 1, and going on up till alpha n. Okay, now I have already proved this, that alpha j is a linear combination of the elements of T. Acha, alpha 1 is a linear combination of only alpha 1, or I can say alpha 1 is a linear combination of T. Acha, how can I say alpha 1 is a linear combination of T? I can write alpha 1 equals to 1 times alpha 1 plus 0 times alpha 2 plus dot dot 0 times alpha j minus 1 plus 0 times beta plus 0 times alpha j plus 1 plus dot dot 0 times alpha n. As you can see, alpha 1 is equals to alpha 1 times alpha 1 and 0 times everything else of the elements of T. So that means alpha 1 can be written as a linear combination of the elements of T set, right? That is obvious. So since alpha 1 is present here also and present here also, so obviously I can say that alpha 1 of the S set is a linear combination of the elements of T. Similarly, alpha 2 is a linear combination of the elements of T. Alpha j minus 1 is a linear combination of the elements of T. Alpha j is a linear combination of the elements of T, that I have already proved. Okay, so this one is a linear combination of the T set, that's already proved over here. Then alpha j plus 1 is again present here, alpha n is present here. So you can see all the elements of S can be expressed as a linear combination of the elements of T, right? So what I am trying to say that is, therefore all the elements of S are linear combination of the elements of T. Okay, and this means that L of S is subset of L of T, right? This is a property that if all elements of a set is a linear combination of the elements of another set, then linear span of the first set is a subset of the linear span of the second set. Okay, that's a property of linear span. Now I want to show that the reverse thing is also happening. That means all the elements of T is also a subset, is a linear combination of the elements of S. Okay, now see how I can show the reverse part. Alpha 1 is present in T and also present in S. So alpha 1 of the set T is a linear combination of the elements of S, just in the same manner. Alpha 2 is a linear combination of S. Alpha j minus 1 is a linear combination of S. Beta, now what was beta? If you remember, beta was C1 alpha 1 plus C2 alpha 2 plus dot dot Cn alpha n. So the vectors here are alpha 1, alpha 2 up till alpha n, that means the elements of S. So I can say that beta is a linear combination of the elements of S, right? I can say this, that beta is a linear combination of the elements of S, because beta was given in this kind of a format. It was in the format of linear combination of the elements of S. So that means beta is a linear combination of the elements of S from this expression. Then again alpha j plus 1 is present over there and alpha n is present on the top. So all those are linear combination of the elements of S. So I can see that all the elements of T are again linear combinations of the elements of S. Okay, so again I can say that all the elements of T are linear combination of the elements of S. So by similar logic, now I can say that L of T is subset of L of S, right? So that means these two together would imply that L of T is equals L of S. Now I know that S is a basis. This was already told to me in the question, right? S is a basis, it's already told. If S is a basis, we know the property of basis is L of S must be equals to the vector space. We already know that because S is a basis. So L of S, that is equals to V, we know that. So that means L of T is equals V, and that's our second condition. So the first condition we had showed that T is linearly independent. The second condition we have showed that L of T equals to V. So the two conditions required to show T is a basis have been fulfilled, right? So I can say that therefore by 1 and 2 T is a new basis of the vector space V, and hence the replacement theorem is proved. Okay. So now I would like to talk about the essence of this theorem that we have proved so that we can do the problem. Just remember this much, that a given vector space can have many bases. Okay, it can have infinite bases. Okay, different combinations of elements, they are going to form different bases, but the property of basis is going to remain same. That means they are going to be linearly independent. Any basis I take, that's going to be linearly independent, and it's going to generate the vector space. These are the two fixed properties, but the bases can be different from each other. Okay, so that's why we are getting different bases as per the replacement theorem. Okay, now if in a given problem we have to replace a vector and form a new basis, okay, then what is the procedure? Just remember, the important part was that we are going to replace only that vector whose corresponding coefficient is non-zero. That means what I am trying to say is, this is the most important part. Cj not equals to 0. If I want to, if this is the given basis, original basis, I want to replace some particular element. Let's say that element is the jth element. Okay, so I have to express the element which I want to introduce in the new basis. Suppose I want to introduce the element beta in the new basis. I have to first of all express beta as a linear combination of the elements of the previous basis. In that expression, I have to figure out which constant is non-zero. Okay, if all the constants are 0, now you can understand, if all the right hand side constants are 0, then beta would become equals to theta, right? Beta would become equals to theta if all the constants on the RHS are 0, and obviously I cannot include theta in a basis. So if beta is equal to theta, it can never be brought into the basis. That's not possible, because then the set would become linearly dependent. Any independent set cannot contain the element theta, right? So all the constants cannot be 0. At least one of them have to be non-zero. Okay, maybe 10, 20, 30 of them are non-zero, and maybe 2 or 3 of them are 0. Okay, anything can happen. Whichever one is non-zero, that element we can replace by the beta element. Okay, suppose the jth constant is non-zero, then I can replace the jth element in the basis by the beta element. Okay, so if I have many non-zero elements, I can replace any one of them, does not matter. Okay, so in continuation to that, let's look at this problem. So it's told that find a basis of the vector space of R3 that are going to contain these two vectors. Okay, now how can I apply replacement theorem here? I know that the standard basis of R3, okay, the standard basis is, let me call that the set S. Okay, let me give it a name S, and I know the standard basis is 1 0 0 0 1 0 0 0 1. Okay, we know this is a standard basis. So since I know this is a basis, now I am going to replace the elements in this basis by these elements and form a basis which contains these two elements. Okay, that's the simple process. So suppose first I want to bring in this term into the standard basis. Okay, let me call this alpha 1, let me call this alpha 2, and let me call this alpha 3. Let me call this as beta, and let me call this as gamma. So initially I want to bring beta into the set and replace it by some alpha. Okay, now we need to make sure how to do the replacement, corresponding to which the constant is non-zero. Just remember that. So initially I am taking that let beta equals to C1 alpha 1, C2 alpha 2 plus C3 alpha 3. So first of all I need to figure out the values of C1, C2 and C3. So let's plug in the values. Beta value is 1 2 0 equals C1 times alpha 1, which is 1 0 0, plus C2 times alpha 2, which is 0 1 0, plus C3 times alpha 3, which is 0 0 1. Okay, now it's easy observation, it's a very easy observation that C1 value must be 1, C2 value must be 2 and C3 value must be 0. Basically these values, because if I put these values in place of C1, C2, C3, then their summation would end up somewhere over here, right? That's simple observation. What I'm trying to say is 1 into 1 0 0 plus 2 into 0 1 0 plus 0 times 0 0 1, that's equals to 1 2 0. Okay, so that's simple observation. Now the important thing is which constants are non-zero. This one is non-zero, this one is non-zero, the last one is 0, so I cannot replace 0 0 1 element to form the basis. Okay, I cannot replace because its constant has become 0. Which elements can I replace? I can replace the alpha 1 element or the alpha 2 element because their constants are non-zero. So whichever one I can replace. So let me replace corresponding to the alpha 1 element. So I can say that since C1 is non-zero, so this implies the new basis would be, I will be replacing alpha 1, right? Corresponding to C1, the vector is alpha 1, so I will replace alpha 1 by the element beta. So this implies, let me call the set T, I am replacing alpha 1 by beta, and alpha 2 and alpha 3, which were the quantities 0 1 0 and 0 0 1, they are going to remain same. So by replacement theorem, this is going to be our new basis. Okay, so this is the new basis. But again I need to do another replacement because I need to bring in gamma into the picture. Okay, now again let me consider that let gamma equals to d1 beta, let me call it C1 only, I will not rename, C1 beta plus C2 alpha 2 plus C3 alpha 3. Now again let's figure out the values. The value of gamma was 1 3 and 1, so I'll put those values 1 3 1. C1 value I need to find out. Beta value is 1 2 0. Alpha 2 value is 0 1 0 and alpha 3 value is 0 0 1. Okay, so now if it is difficult to find out from observation, then let's do the calculation. So this first 1 would be equal to 1 times C1, 0 times C2 and 0 times C3. So that means 1 would be equals to simply C1, then 3 would be equal to C1 times 2, C2 times 1 and C3 times 0. So that means 3 would be equals to 2 times C1 plus C2. C1 value I have already got it as 1. So if I put that, I'll get C2 equals to 1, right? And then moving on with the last one, I'll have 1 equals to 0 times C1, 0 times C2, just simply C3. So I have got the values of C1, C2 and C3. Okay, now again you can see all the constants are now non-zero, so I can replace any one of them, does not matter. Now obviously you don't want to replace alpha corresponding to C1 element, you don't want to replace the first element. Okay, because if you replace beta, then it does not serve the purpose. Then again gamma will be into the picture but beta is not there. We need to keep beta and gamma both into the new basis. That's the requirement of the question. So obviously I'm not going to replace corresponding to C1. I don't want to replace the beta element. I want the beta there. I want to replace from alpha 2 and alpha 3. So I can replace alpha 2 also. I can replace alpha 3 also because both their corresponding constants are non-zero. So let me just replace alpha 2. Okay, so I have that. Since C2 is not equal 0, this implies, let me call the new set, the previous one was T, so let's call that T dash. So T dash would be, since I am doing it corresponding to C2, so I will be replacing the second element by the new element which is gamma, and alpha 3 is going to remain as it is. So this is the new basis. Okay, and this was the requirement of the question, that form a basis which contains beta and gamma. So this is the basis which contains beta, gamma and another element which is 0 0 1. Okay, so this is the final answer to the question. Okay, Thank you. See you in the next video lecture.